Hi everyone, so this is going to be the pre-lab portion of the calcium carbonate experiment. So I'm just going to very quickly go over the type of problems you're going to see in this lab. It's really just limiting reagent problems, and with that there's a couple conversions in there. So just go over them real quickly using this example problem. So you guys can see on the screen, using 15 mils of 0.5 molar calcium chloride and 12 mils of 0.65 molar sodium carbonate, how many grams of calcium carbonate will be produced? Again, one of the classic kinds of chemistry problems. You have different amounts of starting material, and we're going to ask how much we're going to get. So some of the important things we have to use, I'll just go over the conversions first before we get into the actual chem, is we're going to talk about molarity being equal to moles per liter. And the other big conversion that's going to be important is the fact that moles are equal to grams over molecular weight. And kind of a third, you guys should know this one by now, it's just the relation between liters to milliliters. So for those who still haven't fully learned, 1 liter is going to equal 1,000 milliliters. And if you're used to seeing this dimensionally, the other way you'd see this is if I had 5 milliliters, a conversion for every 1,000 milliliters, we'd have 1 liter. And if you guys remember any of your basic math, when you have something over itself, they cancel out. So in this case, if you carry everything through, the mils will cancel out here, and you're left with 0.005 liters. So those are really the conversions we're going to be dealing with today. So to get on with the problem itself, first thing is we have to write the formula out and be able to balance the formula. So we have calcium chloride, and we are going to react it with sodium carbonate. And again, the way the subscripts are put in there, you're just charge balancing. So remember, calcium is a 2+ charge, chloride is a -1 charge, so you need 2 of the chlorides to balance out the 2+ from the calcium. And this is just double displacement like we see in other weeks. The calcium is going to bump off the sodium, and they're going to exchange partners. So what we're left with, I'm just going to write it down here so we get a little more room. We're going to get calcium carbonate and sodium chloride. Now we just have to balance this, and the way that's done, again, just keep accounting for atoms on each side. This one's pretty easy. All you gotta do is put a 2 here, and that's gonna be balanced. Now both of these are solutions, so either through solubility rules or just from common sense, they're solutions that we're measuring out. These are both aqueous. Sodium chloride is also aqueous. And again, that's from our solubility rules, or simply common sense. If I put salt in water, it does dissolve. And calcium carbonate will be our solid. So now that that's balanced out, we got to figure out, well, what actually is going on here. So the way to go through these problems is to figure out how many moles of each I'm using. So again, we're going to use the formulas from above and just rearrange them. So molarity is equal to moles per liter. And we have a concentration in molarities, and we have a volume in liters. We actually have it in mils, we just gotta do a bit of conversion, but it's there. So if I rearrange this to molarity times liters, this will calculate our moles. So this is what I'm gonna do here. So I'll start with the calcium chloride. Again, it's very important you keep track of which ones you're doing. So calcium chloride is 0.5 molar, and we had 15 mils. So again, the quick way of doing this, if you're comfortable with it, is from mils to liters. You move the decimal place 3 spots to the left. So this will be 0.015 liters. And if we calculate that out, we are going to get 0.0075 moles. Now if we do the same thing for the sodium carbonate, again, this one's going to be a different concentration in our example. So this is going to be 0.65 moles, molar, times, and we have a different volume this time. This time it's going to be 12. So 0.012, and this is going to give us 0.0078 moles. So now that we have the moles, we can look at the chemical formula. This is going to give us a lot of information. It's going to tell us where to go with this reaction. Think of the chemical formula like a recipe. It's going to tell you what goes into it and what's going to come out to it. And it's going to tell you the ratios of everything you need. It's for limiting reagent problems. It's similar to having a recipe, having a bunch of excess material. Say you're making a cake and you've got plenty of flour, plenty of sugar, but you've only got, say, 4 eggs. And for every cake, you need 2. Well, you could easily tell me that you could make 2 cakes. It's the same principle for a chemical formula, except we're dealing in moles as opposed to eggs or cups of sugar or similar things. So if we look at the formula, it's going to kind of guide us on what we have to do. 1 mole of calcium chloride. It's an A, I'm sorry guys. We are going to make 1 mole of calcium carbonate. It's also saying for every 1 mole of the sodium carbonate, we make 1 mole calcium carbonate. Now it's not just 1 to 1 to 1. If we do look at the sodium chloride, for example, if we use for every 1 mole calcium chloride, we actually get 2 moles of the sodium chloride. So these are what we call molar ratios, and this is how you go through finding out your theoretical yield, your limiting reagents and everything. Is we're going to basically use these molar ratios to compare one to another. Thankfully for us, everything we care about, these guys right here, are all 1 to 1 to 1, which makes our math very easy for the next couple steps. So now that we have our molar ratios set and we have the moles calculated, we can calculate how much of the calcium carbonate I'm going to make. So we have 2 moles, 2 different reagents, 2 different amounts. So I'm going to walk through both of them first, and we'll see how we pick each one from there. So we'll start with the sodium chloride, and it's very important you guys keep track of which one you're doing. So it's always good to write them down to start. So we know we have 0.0075 moles of the calcium chloride. And now, because of my molar ratios, I know for every 1 mole of the calcium chloride, I make 1 mole of the calcium carbonate. And the way you set up your conversion factor here is, remember, we want those units to cancel out. So this is moles of calcium chloride. So moles of calcium chloride here is going to go in the denominator. And because we're going to get moles of calcium chloride over moles of calcium chloride, they'll cancel out. And that's going to leave us with moles of calcium carbonate. Now, thankfully, everything here is 1 to 1 to 1. So 0.0075 times 1 is going to equal 0.0075 moles. So now we're in moles of calcium carbonate. you guys can see in this case, because everything's 1 to 1 to 1, our mole conversion is going to be the same for the sodium carbonate. That should be a 2 there. Except now we have 0.0078 moles of sodium carbonate. So again, it's just 1 to 1. So without taking up too much room, I'm just going to say that this is going to convert to 0.0078 moles of calcium carbonate. So now I have two values for the calcium carbonate. I have the 0.75 and I have the 0.0078. So how do we know which one's right? So in this case, in most limiting reagent problems, it's going to be the one you run out of first. So when we were setting these up, I didn't tell you guys the whole truth. This is the ideal ratio for these. So this is saying that if I had 0.0075 moles of calcium chloride and I had all the sodium carbonate in the world in excess and reacted it fully, that's the most calcium carbonate I will produce. The same is true, but vice versa for the sodium carbonate. So with that, we're saying that we have 0.0078 moles of sodium carbonate, and we have all the calcium chloride in the world to react it with, which means that our maximum possible yield out of that would be 0.0078. Now, this isn't the case for either of them, but we can see that in both perfect scenarios, we're going to run out of the calcium chloride before we run out of the sodium carbonate because we're making less of the calcium carbonate in the end. So basically, once all of these are used up, and we know we're going to use these in the same ratio, if I react the same amount, in this case, 0.0075, you guys can see, just very simple math, I'd be left with 0.0003 moles extra of the sodium carbonate. So we can say that the calcium carbonate is going to be my limiting reagent in this problem because we're going to run out of that first. It's going to produce the least amount of the product, the calcium carbonate. So now we know how many moles of calcium carbonate we produced. So we're like 90% of the way there to the problem. The problem doesn't want how many moles we had. Moles, again, great for conversions and stuff like that. If you have to weigh something out, though, it's not exactly it. But there is that second conversion we did. So again, remember, we're in moles, so we're almost there. Moles is equal to grams over molecular weight. So we just calculated this. We have this sort of. We just got to go to the periodic table, figure out what the molecular weight of calcium carbonate is. And thankfully for us, it's something easy. It is about 100 grams per mole. So if we take our answer, so we said we are going to produce 0.0075 moles times 100 grams per mole. This will equal 0.75 grams of calcium carbonate. So this right here is going to be our theoretical yield. This is going to be our yield if everything goes right. Now, like many things, some things are not going to go 100% of the way right. The very last thing we need for this lab is a percent yield. Now, the way to think of a percent yield is to think of it like a grade. So what we just calculated is our theoretical yield. Theoretical yield means in a perfect world where 100% of everything reacts and everything goes according to plan, this is how much you can get. Unfortunately, real world is never like it is on paper. Things go wrong, things don't fully react. You spill the solution out, you don't measure quite right. There's different errors that can come in. Your experimental is going to be what you measure. So a percent yield is just your experimental, so what you guys measure, over your theoretical, what you should have got, times 100. So just like a grade, what you got over what it should have been times 100. We've all done this for years. It's how we calculate our grades when we get papers back. Same thing in chemistry, except here we don't get extra points if we go over 100%. There's usually some error we have to account for here. Let's say we got 0.70 grams. Well, we know that so that would be our experimental. And we know we should have got 0.75 grams. So if you do this, you get 0.933 on to infinity. So if we times that by 100, let's point there, we are going to get 93.3%. So a pretty good percent yield. So that's what percent yields are. Again, if you think of them like a grade, they're pretty straightforward. So this is basically what the experiment's going to show. We're going to form calcium carbonate. We're going to calculate how many moles of each we had. And then once we have moles of each, we're going to be able to determine a limiting reagent. Once we have the limiting reagent, that's going to determine how much calcium carbonate we're going to get. And once we have the amount of calcium carbonate we're going to have, we can calculate a percent yield. And that's basically each of the questions you guys are going to have in the post lab for this experiment. And that's basically it. So when you guys are finished with this, comfortable with this, you guys can move over to the experimental video.